Okay, so let's use the concept of momentum conservation to talk about rocket propulsion. We're gonna, for this example, we're gonna make a couple of assumptions, and one of them is that the rocket is already in space. Um, so let's say that we've got a rocket, and the rocket has um, some amount of mass m and some velocity v. So it's already in space. It's got a certain amount of mass and a certain velocity v, and we're going to define um, the right as the positive direction. Once the rocket starts to burn fuel, um, this problem becomes really interesting because, like we were talking about with momentum conservation the other day, um, the rocket's going to push fuel out the back, and there's going to be an equal and opposite force to the fuel pushing on the rocket. That's an internal force, and this rocket, if we assume it's somewhere in deep space, it's an isolated system, so momentum would be conserved. The problem is that when the rocket is burning its fuel, it's getting lighter. It's throwing some of its mass out the back. So we have a velocity that's changing and a mass that's changing. So we're going to set up a bit of notation to help us think our way through this. So at some point later, the rocket is expelling its exhaust. And so the rocket, when it expels its exhaust, it's going to have some velocity that it had before plus some change in velocity. That's going to still be pointed in the forward direction. And the rocket is going to have some mass minus some small change in mass. And I'm going to keep things the same way they're in the book. Your book defines dm as a negative change in mass. So that's something that we're going to want to remind ourselves of as we're working through this. Dm is a negative change in mass, so this quantity here is a small change less in mass. So the mass is decreasing by just a small amount based on the way we defined dm. The amount of mass that's thrown out the back, if we imagine these little particles that are all being thrown out the back, is going to be increasing by an amount dm, and since dm is representing a loss in mass, that's going to be negative dm. And that particle, each of those particles of fuel is going to have some velocity, which your book marks as the velocity of the fuel. We need to keep in mind that the reference frame of the rocket, which is where the fuel is being launched from, is moving. So the velocity of the fuel with respect to the rocket is the thrust, or related to the thrust, but it's not the velocity outside of the reference frame of the rocket. So actually the velocity of the fuel outside the reference frame of the rocket is equal to the velocity of the rocket plus the velocity of the exhaust, which would be in the negative direction. So here we've got our reference frame, the velocity of the rocket plus the velocity of the exhaust, and the velocity of the exhaust is going to be in the negative direction. So the velocity of the fuel with respect to some other reference frame that's not moving is given by that expression. So if the before and after take place in an isolated system, like we said, the momentum would be conserved. And so we have an expression, the momentum initial is equal to the momentum final. The momentum initial was mass times velocity of the rocket. The momentum final is the new velocity of the rocket, the new mass of the rocket, which is just a little bit less. Remember, dm is negative, so that's just a little bit less than the original mass of the rocket, times the new velocity of the rocket, which is just a bit more than it used to be, plus we have to take into account the whole system, so this would be the momentum of the fuel that's ejected. So in that case, we're going to have our negative dm as our small bit of mass that is gaining, positive mass that we're accumulating by launching it out the back, and that's all going to have a velocity with respect to a reference frame outside the rocket of v minus the velocity of the rocket minus the velocity of the exhaust, how quickly we're throwing the fuel out the back of the rocket. So we can expand these terms and we'll get mass times velocity plus mass times dv plus v times dm plus dm times dv minus v times dm plus velocity of the exhaust times dm. One of these terms goes away, and then we've got some other terms that we do need to still consider. Alright, so we're left with that equation there. These also cancel out, so we can get rid of those. And so we're going to get m dv is equal to negative the velocity of the exhaust dm minus dm dv. And at this point, we might be interested in the time rate of change, so we could divide both sides by dt. Or a better way to state that would be to express these as the rate of change with respect to time. So we have dm dt. And then we have an interesting term over here, which is dm dv over dt. This term, your book suggests throwing this term out because it's the product of two very small quantities. And that's a nice physical way of explaining what's going on. A mathematician might be more inclined to describe it as dm dt has physical significance. That is a rate of change, the limit as delta t approaches 0, and that rational expression does not necessarily approach 0. It's the idea behind a limit. Or dv dt. same thing, idea behind a limit. But no matter how we break this up, one of these two terms is left by itself, and the limit as delta t approaches 0 would cause dm, or in the other case, dv, to approach 0. And so this term would be approaching 0. And so we're left with mass times acceleration is equal to the opposite of the velocity of the exhaust times dm over dt. And this is a positive force because remember that dm is negative, so this term here is a negative rate of change of mass. And so this gives us the force of thrust on the rocket, which is negative the velocity of the exhaust times the rate of change of the mass. And what's interesting is that the thrust that we get from a rocket depends on how fast we're expelling the fuel but it also depends on how fast we're burning the fuel. So both of those things matter, the exhaust speed and how quickly we're getting rid of mass. We might also want an expression for the velocity in terms of mass. So we could go back up one step and rewrite our expression where we had mass dv equals negative velocity of the exhaust dm, since that was the term that mattered in the previous expression. And then we can solve for dv, and we'd have dv equals negative velocity of the exhaust dm over m, and we could integrate both sides of that. We're going to have different bounds because we've got a different change of variables between the two sides, but we could have the integral from some initial velocity to some final velocity v of dv, and your book writes dv prime, and the only reason they do that is they don't want you to confuse their final velocity, which they want to just write as v, with the velocity that we were using previously in the derivation. So that prime is just there to differentiate notation. And then we have a negative integral from some original mass to some final mass of the velocity of the exhaust, dm prime over m prime. So again, the primes are just there to differentiate between the variable we were using in the derivation and this variable m that we're going to use to represent our final mass. And when we integrate both sides, we're going to get, in this case, v minus v naught equals negative velocity of the exhaust, and this is the natural log of m evaluated at m minus m. So we can use the logarithm rule to say that that's just natural log m over m naught, instead of writing natural log m minus natural log m naught. And we can also suck this negative sign up into an exponent there, so we get v minus v naught equals the velocity of the exhaust natural log original mass over final mass. And that gives us a nice expression for the velocity.